Okay, cool. Now we're recording, and yeah, we're still working on jump, and obviously we're gonna get to branch soon enough. Cool. So, what we need to do here, we need to keep going. So we have, yeah. So this is signed. Hold on, and so I'm gonna be putting decimal here, just so I know the number correctly. Percent sign D. Cool. So what is the number? Minus 66. So off by a factor of like 2-ish. Because 64. Oh, because the last one also has to be. Last bit also has to be a. No, last bit must be a 0 because it's an even number. So, okay, I'm just going to have to move that over a bit. Whatever. Cool. NVIM CPU. Yep. So let me continue editing the test bench so that we can, have this keep going. And so that's 66. So that should be 34. And then we obviously have to add 2. So 32. So, that one's. Yeah, that would be 32. 16, 8, 4, 2. Okay, hopefully that number is correct. Minus 36. Okay, so now we need to increment it by 4. So that would be this bit theoretically. Dot slash compile, dot slash test. Cool. Minus 40. Okay. NVIM CPU test bench. Okay, hold on. Maybe that one's correct. Let's just compile, dot slash test. Minus 2082. Okay, so that one is in fact wrong. NVIM CPU test bench. So this one is in fact wrong. And so we have to edit this one. And obviously this one has to be. Bring it down a little bit. Dot slash test. Minus 20. Now we just need 12. Okay, so now. Oh. I had a very classic off by 1 error. Minus 32. There we go. Now, of course, this is not actually done there. CPU test bench. And then how do I have it? How do I treat it like a signed number? Verilog. I should probably zoom this in. Verilog do signed addition. Yes. Yes. Cool. There we go. A plus B is not an overflow, whatever. I don't care about that. You have a signed overflow if both inputs have the exact same sign and the result has an opposite sign. I don't care about signed overflow. I did this with unsigned numbers, yes. Now they're signed, but I get the proper value, but display is what. Okay, hold on. Output reg signed AB. Okay, so CPU.v. Okay, so in essence, we should set instruction pointer as signed. Because that looked like it was automatically unsigning it. No. We are trying to add negative 32, and it's not adding negative 32 properly. Because 48 minus 32 and Vim CPU, okay. So instruction pointer and immediate J are both signed numbers, right? Cool. And so why is instruction pointer not a signed number here, right? Hold on. Signed arithmetics in Verilog, yes. All operands must be signed. If any of them are unsigned, it will get automatically converted to signed. Ah. So what I need to do, nvim instruction decode.v output signed immediate J. Well, no, clearly that worked. Ah, whatever. Because immediate J is signed here. I don't know. let's just do this. Instruction pointer minus equals, I don't know, 100,000. And let's just print out the instruction pointer here. I need a dollar sign. Hold on. Yeah, let's just print out the instruction pointer here and let's see where we go, right? Instruction pointer. $compile, $test. Instruction pointer, big number. Because we're subtracting. And it's a big number. Wire. Ah, register. Signed register, yes. Theoretically, this should work. It is not going to 16, it's going to 20. Because minus 32. Oh, because we're automatically doing the plus 4? Yes, because we're automatically doing the plus 4. So what we need to do is just a minus 4 in here. Minus 4. Cool, there we go. So now we have jumps working properly, and they're doing stuff with offsets, and we're looping. It's very nice. It's very nice. It's a nice CPU, very nice CPU. It's the greatest CPU, right? Cool. So what we need to do from here is we just kind of have to keep going, right? Keep going here. So nvim CPU.v. Yeah, okay. So now we have to do branch. Now we work on branch, right? So yes, nvim instruction decode. Right. So instruction decode branch. I already have a branch thing. I need to add comparisons to my ALU. Hold on. Let's go over to the code. Yep. If the two things are the same or different, yep. So ALU.v. Cool. So we need multiple outputs. We need a we take func3, func7. So we only look at func3 for this, right? So we do we have 1, 2, 3, 4, 5. We have 6 cases, whatever. Unsigned. Oh, well, okay. We'll ignore the unsigned for now, right? We'll deal with unsigned later. These should be signed inputs. That should not be signed. The input data should be signed. Because we're assuming everything is signed here, right? Add is signed. It's all signed. It's all signed, okay? We love signedness here. Cool. So we need a few more outputs here. Out, and then should branch. And then output should branch. And so here, when we do the assign here, assign should branch. So based on func3, yep. Func3, if it's 0, question mark, then what we do is we return the bit that is for if value 1, input data A, input data A equals input data B. Otherwise, we return 0. Cool. And so yank $. And then now let's just do the next one. So we have func3 equals 1. And then 1 is not equal to. Cool. Paste this down. Then we have 4, 5, 6, 7. 4, 5. We're not doing unsigned. So we're not going to do unsigned. So here is, we have 1 for less than, and 1 for greater than equal to. Cool. So we have should branch as an output. Then CPU.v. In here, let's just have a wire for should branch. Should branch. And then let's feed that into ALU. We have should branch. Cool. So, yep, should branch, should branch. Does the ALU actually use the clock? No, it does not use the clock, so we will ignore the clock because we're not using it. And obviously the ALU, we're going to ignore the clock because the ALU is just an ALU, you know? Cool, so we have our ALU here. And so we have our should branch. So we have an if jump, and then we do this. Then if branch and should branch begin end. Then what we do in branch, we just do PC plus equals immediate. Okay. So we just do PC plus equals. What is the branch immediate? Branch is B format, which is literally just a left-shifted version of the I format. So instead of immediate J, I'll do immediate I, and I'll just manually left-shift it by 1. Left-shift by 1. No, that's incredibly jank, actually. No, is it? Yeah, I think that's incredibly jank. I should probably output it in immediate... whatever. Yeah, I should probably output immediate B. Cool. And so immediate B is a new wire we're going to be adding here. It's a signed version here. Signed. Immediate B. And then... Oh, wait, hold on. CPU.v. And then, obviously, in instruction decode, immediate I, immediate J, immediate B. Cool. And in our instruction decoder, instruction I, instruction J, immediate B. Obviously, this immediate J is no longer supposed to be a thing. Because, again, this is just like bit manipulation. We don't actually particularly care. Immediate B. Right? Cool. So now we have immediate B. Immediate I is this. Immediate B, because we are trying to guarantee a 0, we're just appending a 0 to the end of this, comma, instruction. And so obviously for the branch, instruction of 4, 0, 1, 2, 3, 4. Yeah, checks out. Instruction of 4:4. Cool, so that's immediate B. Hold on. 31 to 20 for I type. Oh, hold on. It's actually a whole format. Okay, hold on. 12. Okay, this is actually... So instruction of 31. Hold on, 31. Comma. Instruction of 7:7. Of 7:7. Comma. Now we go 10 to 5. So it's 30 to 25. Instruction of 30 to 25. And then it's instruction of 11 to 8. And that has 4 things. Yep. Yep, okay, cool. So that should be instruction B format. Wild setup there, but whatever. Write back should not be enabled. So if it's a B format, so write format, we write back, hold on. So write back should be 0 if it's a B format. So hold on. I'm just going to add a format, just wire. I'll add it as an output. Write back format. And so output, I'll give it, we have 6 formats here. We have 6 formats. 6:0. I'll just give it a, I'll make it 8. I'll make it 8 bits. 7:0. As you do. And an FMT. Cool. And so assign write back equals FMT. Hold on. Format not equal to, so we, in R type, obviously we write back in all of these because we have an RD, RD, RD. So in RI, then RI J RIJU. Okay, RIJU. So format not equal to R, which I'll set this as the order. So so 0. So not equal to SOB. SOB is the ones where we don't write back. So S not equal to 2 and format not equal to 3. Right? Cool. Now we have to actually write into format. So opcode 2 and 6 for jump. 2 unique here and 6 unique here. So jump is hold on. Oh boy, I do not want to pull up a K map. I do not want to pull up a K map. That's not something I want to do. So, I'm just gonna have a. I'm not gonna have format. I'm not doing format. We deal with that later. We'll just manually figure out right back here. So it just can't be any of. It just can't be anything in this section. So hold on. Okay, this is actually kind of annoying. Because obviously, these 2 bits are always 1. These 3 bits are kind of perpetually 0. So we just expect a 1, 0, 0 in that area. 1 and 3 zeros. Yes, and that's a write back indicator for branch or store back. So we're going to do a instruction of 0, 1, 2, 3, 4, 5, 5 to 2. 5 to 2 is not equal to, and then that's just 8. Cool. And so then write back is coming from here. Good, good. And we should be good here. Yeah, I think this should be good here. So then what we have to do is, let's make sure I didn't break anything else. We are still working. 553, 16. We're chilling. We're chilling. Cool. So now let's do some stuff here. Let's just add a quick loop. I don't know. Before the jump. Yeah, before the jump. Where let's, because this goes back to 16, which is over here. So I don't actually particularly care. I'll just set up the values here, right? We'll count down instruction of 4, let's say. So then instructions of let's just go 12 equals 32 bits. And so the instruction we want here is a branch equals, so a branch greater than or equal to, right? So we have branch greater than or equal to, and let's say 5, just random number 5, right? So BGE greater than or equal to, and so we don't have an RD, we have, so greater than or equal to, we have RS1, let's say it's x1 greater than, sure, x0, branch greater than or equal to x1, not x2, x1, and so it should run 31 times, x2, x1, and then if that is the case, we should go back 12. Cool. So, and if it's not the case, we keep going. So, and obviously we need one in here. That's just a very nice sub I. Do I have sub I implemented? This is a sub I is not a thing in RISC-V, so it's obviously not implemented. Greater than or equal to, oh, let's just add 1 to x1, whatever. Add I x1, comma 1, comma x1. Cool. So I'm just gonna yoink this, paste it in here, add I xi, comma 1, comma not xi, x1. Cool. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. Func 7, func 3. Then add I. Yep, I format. I format. Oh, it's just opcode RD and then func 3, right? Opcode 1, 2, 3, 4, 5, 6, 7. RD should be 1. 1, 2, 3, 4, 5. Yep, that's x1. Then we have func 3, 0, because it's add I. Then we have x1 as always 1. 1, 2, 3, 4, 5. And then for the number, we're just adding a very nice 1. Cool. So adding 1 to there. And then now we build up this one. And it should go back, probably not to start. It should probably just go back 1. So minus 4. Cool. So B format. So opcode for BGE is 11000111 11000111. Cool. So there's our func 7. Then we have immediate, because it's negative. I'm just gonna set the immediates to all be 1s to start, and we'll deal with it later. So 7, 8, 9, 10, 11. Let me just add spaces here so I'm don't kind of stay sane. Func 3 for branch greater than is 5. So 5 is 101. Correct? Yep, func 3, 101. None of these numbers are greater than 8. Yep. Cool. Our S1 is going to be x2, so 00010. Our S2 is going to be 1, 1, 2, 3, 4, 1. Then the immediates, I'm just going to set it to all 1s. 1, 2, we should see 6, 7. 1, 2, 3, 4, 5, 6, 7. Cool. So, which one of these gets set? Because we're just going back minus 4. So it should be this one is 0. And that should be our instruction. And so this bit should run like a decent amount. So obviously we have to increment these numbers. 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48, 52, 56. Cool. Compile, test. Okay, it's going. So 16, 12, 16, 12, 16, 12, 16, 12, 16, 12. It's not running enough, but what are we seeing? We're seeing this number does in fact increment 1 by 1, which is good. So that... Oh, yeah, because we... Yeah. So what we need to do is we don't let it run for 60. We have it run for 120. Pile, test. It is in fact going up there. 16, 12, 16, 12, 16, 12. And so 31, 31, 32, 31, 16, 20. Okay, so it does, when it's greater than, we do in fact iterate up. Branch greater than or equal to. This here it is equal to. Okay, so I need to double check my BGE to make sure it's like correct. 32, 31. Then we just do a whole bunch of arithmetic, which we know is correct, and we just continue looping there as our main loop. Cool. Okay. NVIM ALU. Branch greater than or equal to. If it's equal to 5, yes. So that branch was in fact correct. But it was acting as if though it was only greater than. Because by the time we branch, they should be equal. Correct? NVIM. Right, because by the time we branch... Why does it look like this thing has 1 less bit than the other ones? Huh? Hold on, hold on. 1, 2, 3, 4, 5, 6. 1, 25. We should have 1 more bit there. Do we still continuously loop there? Yep. 31, 32, and then we go. Why? Because x1 is equal to x2, right? So this is correct. Wait, but then what was that 0 for? Hold on. 1, 2, 3, 4, 5, 6, 7. Yep. Then we have a section here, which has 11, 1. So that's 2. Huh? Oh, hold on, hold on. Yeah, so that's 2, 4. Right, that's good, that's good. And so this should be 5 long. Right? 2, 3, 4, 5. Cool. Then what we have after that is func 3, 101. Yep. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, that's correct. That should be correct. I see no problems with that. Why is this branch greater than, not greater than? Oh! Oh, no, that's correct. It's waiting for the left stand. Yeah, because it keeps going on a negative signal. No. This is me not understanding programming. Whoopsies. Whoopsies indeed. Cool. And so we're looping through that bit of the loop. So we have a while loop that iterates, which is very nice, actually. Very nice. So that's basically all of branch done. Now we need unsigned. So, let's get unsigned done. So signed, input signed. Then I will have wire unsigned with -1 colon 0. And so unsigned input data A, unsigned input data B. Cool. So that's just a wire, and so this is so we can treat it as unsigned. And I'll assign unsigned input data A as, and I'll just assign it to input data A. Input data A. Cool. And then you paste that down, and this is going to be B, and this is also going to be B. Cool. And so now we can actually 4, 5, 6, 7. And so 6 and 7 are effectively identical to that, except it's unsigned. So unsigned underscore less than unsigned underscore, and then obviously we do the same thing here, which unsigned both. Unsigned, and here we'll also go unsigned. Cool. So, and obviously it's 0 if none of those cases are there. Cool, so now we have unsigned numbers. I should probably also implement the base instructions. So, hold on. Let me clean up this bit, because I know for a fact we almost certainly do not need this many brackets. If func3 is 0, then we do that. Hold on. Hold on. So I'll have the colon at the end. Func3, func4. Yep. 4, 6, 7, 0. Cool. And so obviously we have and, or, XOR, left shift, right shift. Yeah, okay, so left shift is at 1. Func7 is 1. So we left shift by that much. Then right shift is at 5. And we do right shift. Cool. Then right shift arithmetic. So most significant bit extension. Hold on. How to do MSB extension right shift Verilog. Shift operator, yes. How do I logical fill with 0? Ah, it's triple. Amazing. Wait, no, not there. Cool. And so that's actually a very nice thing to see. And so what we see is we need 5. Oh, func7 is 20. Ah, okay. I'll just have it in here. Funct7 equals no what? Nah. I'll deal with it in a good way here. So if it's that, then what we do is we indent it one more layer down here. Then obviously we can just, because where's end? Oh, there we go. Cool. And obviously there. And so that should be good. And so let me paste this down here and wipe this. So func7 is, and so where are we here? Yep, func7, if it's 0, we just do a normal right shift. Otherwise, we do a keep the sign right shift. Cool. And then shift left stand is just 2 and 0 extends. What? Hold on. Set less than, and then 0 extends the set less than. What does 0 extend the set less than mean? Huh? Okay, hold on. Let me yoink this here, paste it down here. Let's just do normal set less than. Or is hold on, this is 2. It's going to be set to less than, and then here I'm gonna just have another set of parentheses so I can like keep it nice and neat. Question mark 1:0. Sure. And I do not particularly care about 0 extending. Oh, it's unsigned. Okay, there we go. That's the difference. And so that's just at 3. Cool. So at number 3 here, we do unsigned less than. So unsigned input and unsigned input here. Cool. So now we support all of the arithmetic operations, all the other format operations. We support all of the branch operations. We support the jump operations. Now we need to support the immediate operations. Yes. And so these immediates, so func3 is the same here, XOR immediate same, or immediate same, and immediate is the same. So func3 is there the same. Shift logical left, same. Shift right logical is the same. Right arithmetic is... Yes. Oh, the immediate... Okay. Sure. So these 3 are evil. But, okay then, sure. And then these 2 we just have set. Like, those just work. So, I want to support all of the immediate instructions as well. Before we move on to memory, right? So I want to support the immediate instructions. Cool. So, what we need to do here at this point is we just need to... Oh, hold on. I should probably do this. We do have the capability to do all branch instructions. This should be build the capability to do all... Oh, hold on. It's not typing there. All immediate instructions. Cool. So we want to build the capability to do all the immediate instructions. Cool. So now what we have to do... Yeah, we just have to keep going with the immediate instructions. So we have... right, left. Okay, so we just need shift logical left, shift logical right. And, oh, hold on. Let me edit the stream title. Today we make it branch and do all immediates. Cool. Amazing. Great success. And so, yeah, we have to do the whole nonsense over here. And I think that nonsense happens in instruction decode. NVIM. Well, I mean, this is just the immediate bit, right? Yeah, store byte. Yeah. Word, half word. And then... No, it's not just the immediate bit. It's some bit, whatever. Store word is just store the entire word into memory. I want to have an artificial memory here that I'm going to use for testing. I'm probably going to make it like a whole cache flow thing. Yeah. And obviously, I'm not going to deal with environment call and environment break just yet. That's a bit. Hold on. Let's look at the RISC-V unprivileged. This is everything in here. Hold on. So, RISC-V privileged. Instruction. Control, status ISO, machine level ISO. Whole lot of stuff. We're actually really close to supporting the entire base RISC-V thing. All we need is memory, right? Being able to load and store. And all we need after that is... It's just load and store. Like... Hold on. After today, all we need is load and store, and then we will be able to support the entire RISC-V ISA. Huh. Okay. Okay, then. We just need... That's actually insane. We're almost done. At least the base ISA. We also have the multiply, the atomic extensions, the D floating point? Oh no, it's just floating point. We have multiply, we have floating point, we have... No, we're not doing compress. That's nonsense. And the pseudo instructions are just compiler nonsense. Yeah! What does format star mean? Huh? Okay, that's... Whatever. And yeah, I mean, obviously registers, that's just convention in the compiler. We don't actually have to worry about that as the CPU designer. Right? Okay. Atomic swap. Okay, so this is a little bit more work, but we'll get there eventually. R format. Oh, there's repasting R format. It's so much R format stuff. Whatever. Cool. So I need to have it figure out how to do this. Shift left logical immediate. Okay. NVIM CPU to let's do this in instruction decode, right? I'll instead of write back, I'll do the immediate immediate I format, and then it's just 5 to 11. Hold on. I don't need a new format there. Because I format is by default. Hold on. In immediate I, I'll set this to signed. So we can, add and subtract negative numbers by default, whatever. So what we need to do here is we need to set in A. So it's val or immediate. And so opcode of 5. 0, 1, 2, 3, 4, 5. That bit is a store byte, whatever. We don't actually particularly care about. That we'll have to do that in a bit, whatever. What? When we're doing branch, we're comparing against immediate. Huh? Okay, but I'm changing this from opcode of 5. 0, 1, 2, 3, 4, 5. Yeah. Why was this... Oh, because we're not writing back at that moment in time, so it didn't actually matter what we were feeding in here for branch. Yeah, okay, that didn't matter. And jump and link. That just, we also don't care. We don't go through the ALU for that, so that's whatever as well. Cool, so that's actually pretty easy to figure out why. So opcode of 5 for that actually kind of makes sense. And so if it is opcode of 5... Oh, if opcode of 5 is true, then we're doing val b, yep. Otherwise, we're doing... Yeah, so otherwise we're doing the immediate I. And so in immediate I, what we need to do is we need to check if... Ooh. We need to check if it's 5 or 1. Yes. And then, so we need to do a check here, question mark, for if opcode, so not opcode, funct3, funct3 equals 5, or funct3 is 1. if it is that, then we basically set, we feed it in immediate of 0 to 4. Yes. Not 0 to 4. We're looking for 4 to 0 because everything here is top to bottom, right? Cool, because it's shifts. We can do that for shifts. And then we also need to edit the ALU func3. So another register. Func3 ALU func3. I'll use an underscore here. Cool. And so this would probably all be instruction decode. There's a whole bunch of mess here. But yeah. Assign ALU func3 is equal to func3 is 5. So we're looking for opcode of 5 and func3 is 5 or func3 is 1. So in the case where we'll be using immediate 4 to 0, we will, so if that's the case, it will be immediate, it will be immediate of 0x20. Oh, func7. Oh, this removes func7. If that's the case, we'll just use that as func7. Okay. Well, I mean, we're just feeding it in as func7 anyways, right? Because, right, because, yeah. Okay, so we shouldn't have to do anything here then. Because we just have func7 do func7 stuff. Cool. Nvim ALU dot v, and then obviously func7. We should not be checking, yeah, 0 or not 0. Yep, func7, and then obviously 4 to 0. Yeah. So we do now support every single thing except for memory instructions. Cool, that's actually hype. I'm gonna leave this stream here for now. And next time we will do memory instructions. See ya.